Example 5.34 is another application of U-substitution, but this time notice we are not working with a indefinite integral because we have bounds on the integral. We have the lower bound of 0, upper bound of 1. So we're not going to use a plus c in this case. We will use the bounds and then finish it off with the fundamental theorem of calculus of part 2. In order to integrate this, we do need to use a U-substitution, so we will let u be the innermost function. So to me that looks like 1 plus 2x cubed. Then we'll find du. We'll look to see if we have our du perfectly fit into our function, and oops, I forgot my square on there. And we almost do. We just have the 6 factor as an extra, so I'll divide through by 1/6, or sorry, multiply through by 1/6, so that I have 1/6 du is equal to x squared dx. So we can go through and rewrite our integral. In my parentheses, I now have u, and that's raised to the 5th power. The x squared dx will be replaced with a 1/6 times du. Now the only thing left to deal with is the bounds. And you have two options. You can evaluate your integral in terms of u with no bounds, treat it as an indefinite integral, find the antiderivative, then go back and finish it off in terms of x, or you can convert the bounds. Let's go ahead and find out how to convert the bounds. I wouldn't want to copy over my lower bound of 0 onto my new integral without giving it some thought. And that's because 0 was a value for x, not necessarily a value for u. So we have to ask ourselves, if x is 0, what would u be? Well, remember that u is the function 1 plus 2x cubed. So u with 0 plugged in would be 1 plus 2 times 0 cubed, which results in 1. So the old case, where x was 0, needs to be replaced with the new value for u. U is equal to 1. And then we need to do that for the upper bound as well. If x is equal to 1, what would u be? Well, that would look like u evaluated at 1. That becomes 1 plus 2 times 1 cubed, or 1 plus 2, which would become 3. So our upper bound on the new u integral would become 3. And then we can evaluate this as a typical definite integral. So we'll have 1/6 times u to the 6th power divided by 6, evaluated between 1 and 3. Notice there's no need for a plus c here because we're doing a definite integral rather than an indefinite integral. Let's clean that up before we evaluate u to the 6th power over 36, and we're going to evaluate from 1 to 3. Now notice these are u values. There's no need to go back to x. And that's good life advice in general. Don't go back to your x, right? So we are in terms of u. We've moved everything into this new frame where we are evaluating between u values. We don't have any x's left. So let's go ahead and keep moving forward. U to the 6 over 36, that would become 3 to the 6th over 36, minus, when we plug in 1, we have 1 to the 6th power over 36, and we can simplify. I can't think of 3 to the 6th power, so let me grab my calculator. That's 729 over 36, and while I have my calculator out, let's check to see if that simplifies. 729 over 36. Sure does. Turns out to be 81 over 4. But don't forget there was a second fraction there, so minus 1 over 36. Ooh, maybe we simplified too soon. I need those common denominators, right? So that's going to turn into 728 over 36. Let's see if that simplifies. It does. It comes down to be 182/9. So when we do a U-substitution for a definite integral, we need to make sure to take the time to convert our bounds because we don't want to plug in values for x into a variable like u. Our next example, 5.36, involves a definite integral where we need to use U-substitution that involves a trig function. So again, first thing we'll do is let u be equal to some function of theta, and we want to pick the innermost function. So of cosine squared, we can consider squared the outside function and cosine theta the inside function. Then du would become negative sine theta d theta. Looking back at our original integral, that U-substitution doesn't work. So instead, we're going to throw that out, and we're going to think of trig identities. Think back to your trig class, your pre-calc class, or wherever you've practiced trig identities. There is a relationship between cosine squared theta and the ratio 1 plus cosine 2 theta over 2. So the first thing we're going to do, after we've recognized that a U-substitution right out of the gate is not helpful, is we're going to rewrite our integral, still keeping everything in terms of theta so far, but instead of cosine squared, we'll write 1 plus cosine 2 theta over 2. Now from here, we can use a little bit of algebra to clean it up. We have two terms, 1 and then plus cosine 2 theta. Integrating the 1 is a piece of cake. However, integrating the cosine 2 theta, that requires a U-sub. It's a very tiny U-substitution, so it's not that difficult. However, it's needed. So cosine of 2 theta. The 2 theta is that inside function. So we'll let u be equal to 2 theta, then du would be 2 d theta. Now, I don't have a 2 d theta in that integral that we're using a u substitution on, so I'll divide the 2 off. I do have a d theta, so I can replace d theta with 1/2 du. So let's do our scratch work over here. Our integral is now going to be 1/2 cosine u times 1/2 du, or we can write that as 1/4 integral cosine u du. We know the integral of cosine is sine, so we'll have 1/4 sine u. And I don't have any bounds on here, so I would call that an indefinite integral, say that it's plus c. And then we have our choice. We can replace u with the function of theta. So we could write this as 1/4 sine 2 theta plus c. And we can say, oh, well, now we know the antiderivative for that function. We can use the fundamental theorem of calculus to evaluate between the bounds 0 and 2 pi. So let's bring down what we have. From that first term, integrating 1, we got 1/2 theta because there was a 1/2 multiple out front. From the second term, the 1/2 times cosine 2 theta, we found the antiderivative, 1/4 sine 2 theta plus c. We don't need to write the plus c though, because we know we're evaluating between theta equals 0 and theta equals pi over 2. And when we do definite integrals, the plus c disappears. So evaluating with our upper bound first, we'll have 1/2 times theta when theta is pi over 2 plus 1/4, oh, that looks messy, sine 2 times pi over 2 minus 1/2 times 0 plus 1/4 sine at 2 times 0. And we'll clean that up. 1/2 times pi over 2, that's pi over 4. Sine at pi is just 0. 1/2 times 0 is 0. And sine at 0, 2 times 0 is just 0. So sine at 0 is also 0. Got a lot of zeros in this one, and our final answer would be pi over 4.